Question 1. Consider a scenario where a property owner requests approval for a new septic system installation on their rural property. The owner provides a design plan and states that a similar system has been successfully used on their family's property in a different state for many years. The installer is experienced and has a good local reputation. The property has clay-rich soil with a high water table, and the proposed system design appears to be a basic, older model that may not fully meet current local setback requirements from wells or surface water bodies. As a certified water treatment specialist, what is the most appropriate course of action? Option A. Conduct a thorough site-specific evaluation to ensure the proposed design and installation fully comply with all current state and local regulations for on-site sewage disposal systems, regardless of the owner's assurances or the installer's reputation. Option B. Prove the system based on the owner's assurance that a similar system has worked elsewhere and the installer's good reputation, assuming it will likely be adequate. Option C. Advise the owner to install a less expensive, simpler system that is easier to manage, even if it falls slightly below the most stringent regulatory requirements, to save them money. Option D. Recommend the owner proceed with the installation of the older model system, as it is a proven design, and address any minor setback issues with the local health department on a case-by-case basis after installation. The correct answer is A. Conduct a thorough site-specific evaluation to ensure the proposed design and installation fully comply with all current state and local regulations for on-site sewage disposal systems, regardless of the owner's assurances or the installer's reputation. Explanation. Scenario analysis. This scenario presents a common challenge for water treatment specialists, balancing the immediate needs of a property owner with the long-term public health and environmental protection mandated by regulations. The challenge lies in the specialist's responsibility to ensure compliance with established standards for septic system design, installation, and maintenance, even when faced with pressure to expedite or approve a potentially non-compliant solution. Failure to adhere to regulations can lead to environmental contamination, public health risks, and legal repercussions for both the specialist and the property owner. Correct approach analysis. The correct approach involves a thorough review of the proposed septic system against the specific requirements of the relevant state or local health department regulations governing on-site sewage disposal systems. This includes verifying that the system design meets the criteria for the soil type, site topography, and expected wastewater flow, as well as ensuring that the proposed installation methods and materials comply with approved standards. The specialist must also confirm that the maintenance plan adequately addresses the long-term operational needs of the system to prevent failure. This approach is correct because it directly upholds the regulatory framework designed to protect groundwater and surface water quality, prevent the spread of waterborne diseases, and ensure the longevity and effectiveness of the septic system. Adherence to these regulations is a fundamental ethical and legal obligation for a certified water treatment specialist. Incorrect approach is analysis. Approving the system based solely on the property owner's assurance that it has worked elsewhere is a regulatory failure. Septic system performance is highly site-specific, dependent on local soil conditions, groundwater levels, and climate, which vary significantly. Works in one location may be entirely unsuitable and non-compliant in another. This approach bypasses the essential site evaluation and design review mandated by regulations. Accepting the system based on the installer's reputation, without independent verification of compliance, is also a regulatory and ethical failure. While a reputable installer is valuable, their work must still meet the established technical and regulatory standards. Relying solely on reputation absolves the specialist of their duty to ensure the system's compliance with public health and environmental protection laws. Recommending a system that is known to be less stringent than regulatory requirements, even if it is cheaper or easier to install, constitutes a direct violation of the specialist's professional responsibilities and the governing regulations. This approach prioritizes expediency or cost savings over public safety and environmental integrity, which are the core tenets of water treatment and on-site sewage management. Professional reasoning. Professionals in this field must adopt a decision-making framework that prioritizes regulatory compliance and public health above all else. This involves 1. Understanding and internalizing the specific regulations applicable to the jurisdiction. 2. Conducting a comprehensive site assessment to gather all necessary data, soil type, topography, setbacks, etc. 3. thoroughly reviewing the proposed system design and installation plan against these regulations. 4. Verifying that the proposed maintenance schedule aligns with best practices and regulatory requirements. 5. Communicating clearly with the property owner and installer about any discrepancies or required modifications. 6. Documenting all assessments, decisions, and communications meticulously. 7. Never compromising on regulatory standards, regardless of external pressures or perceived convenience. Question 2. The risk matrix shows that surface water entering the treatment plant has a high likelihood of containing turbidity, coliform bacteria, and dissolved organic matter. Considering the absolute priority of public health and regulatory compliance, which of the following treatment approaches best addresses the immediate and most critical risks? Option A. Focusing on removing turbidity through sedimentation and filtration, as it is a visible indicator of water quality. Option B. Implementing a robust disinfection process to address coliform bacteria, as they pose an immediate and severe public health threat. Option C. Implementing a multi-stage filtration process to remove turbidity, followed by disinfection to eliminate coliform bacteria, and then advanced oxidation to reduce dissolved organic matter. Option D. Prioritizing the reduction of dissolved organic matter through activated carbon adsorption, as it can contribute to disinfection byproduct formation. The correct answer is C. Implementing a multi-stage filtration process to remove turbidity, followed by disinfection to eliminate coliform bacteria, and then advanced oxidation to reduce dissolved organic matter. Explanation: this scenario is professionally challenging because it requires a water treatment specialist to interpret a risk matrix, which is a tool for prioritizing potential issues based on their likelihood and impact. The challenge lies in accurately assessing the potential impact of various impurities on public health and regulatory compliance, and then selecting the most appropriate treatment strategy based on that assessment. Careful judgment is required to balance the effectiveness of treatment options with resource constraints and regulatory mandates. The correct approach involves a comprehensive evaluation of the identified impurities against established drinking water standards and potential health risks. This approach is right because it directly addresses the core responsibility of a water treatment specialist, ensuring the delivery of safe and compliant drinking water. Specifically, it aligns with the principles of public health protection mandated by regulatory frameworks such as the Safe Drinking Water Act, SDWA in the United States, which sets maximum contaminant levels, MCL, and treatment techniques. By prioritizing treatment based on the severity of the risk posed by specific impurities, the specialist ensures that the most critical contaminants are addressed first, thereby minimizing public health exposure and avoiding regulatory violations. This systematic, risk-based approach is a cornerstone of effective water management. An incorrect approach would be to prioritize treatment based solely on the ease of removal or cost-effectiveness, without a thorough understanding of the associated health risks and regulatory requirements. This fails to acknowledge the absolute priority of public health and regulatory compliance. For instance, focusing only on physical impurities like turbidity might seem straightforward, but it overlooks the potentially severe health impacts of biological contaminants like Giardia**, or chemical contaminants like lead, which are subject to stringent MCLs and pose significant health threats. Another incorrect approach would be to address impurities in the order they appear in a general list without considering their specific concentration, source, or potential for harm. This lacks the critical risk assessment necessary for effective water treatment and could lead to inadequate protection against more dangerous contaminants. Professionals should employ a decision-making framework that begins with a thorough understanding of the water source characteristics and the potential impurities present. This should be followed by a comprehensive review of relevant regulatory standards and guidelines. The next step involves assessing the risk posed by each impurity, considering both its potential health impacts and its likelihood of exceeding regulatory limits. Based on this risk assessment, treatment strategies should be developed and prioritized, ensuring that public health and regulatory compliance are the paramount considerations. Regular monitoring and reevaluation of treatment effectiveness are also crucial components of this framework. Question 3. Risk assessment procedures indicate that a water treatment plant is experiencing fluctuations in several key water quality parameters. The plant operator has noted a slight increase in turbidity, a decrease in dissolved oxygen levels, a noticeable change in taste and odor, and a slight drop in alkalinity. Given these observations, which of the following actions represents the most critical and immediate priority for ensuring public health and regulatory compliance? Option A. Conduct a comprehensive review of historical data for all parameters to identify long-term trends before taking any action. Option B. Initiate immediate investigations into the cause of the increased turbidity and the decreased dissolved oxygen, and implement corrective actions to restore these parameters to acceptable levels as per regulatory standards. Option C. Focus on identifying the source of the taste and odor issue and implement aesthetic improvements to enhance consumer satisfaction. Option D. Increase the dosage of chemicals used for taste and odor control to mask the detected changes. The correct answer is B. Initiate immediate investigations into the cause of the increased turbidity and the decreased dissolved oxygen, and implement corrective actions to restore these parameters to acceptable levels as per regulatory standards. Explanation: this scenario presents a professional challenge because it requires a water treatment specialist to interpret and apply water quality parameter data in the context of regulatory compliance and public health protection, without the benefit of direct, immediate laboratory confirmation for all parameters. The specialist must make informed decisions based on available information, understanding the implications of deviations from established standards. The challenge lies in balancing operational efficiency with the absolute necessity of ensuring safe drinking water. The correct approach involves prioritizing actions based on the potential immediate risk to public health and the likelihood of regulatory non-compliance. This means addressing parameters that have the most direct and rapid impact on water safety and are subject to stringent, immediate regulatory limits. For instance, high turbidity can indicate a failure in filtration and a potential pathway for pathogens, while significant deviations in pH or alkalinity can affect disinfection efficacy and lead to corrosion. The regulatory framework for drinking water quality, such as the EPA's Safe Drinking Water Act, ESTWA in the U.S., mandates specific maximum contaminant levels, MCL, and treatment techniques that must be adhered to. Promptly investigating and rectifying issues related to these parameters is a direct ethical and legal obligation to protect consumers. An incorrect approach would be to focus solely on parameters that are less immediately critical to public health or are primarily aesthetic, such as taste and odor or color, when more serious issues are indicated. These parameters are important for consumer satisfaction and can sometimes signal underlying problems. They do not typically pose an acute health risk in the same way that a lack of effective disinfection, potentially indicated by low dissolved oxygen or high turbidity, or the presence of harmful contaminants might. Another incorrect approach would be to delay corrective actions pending further, non-urgent testing for parameters with less immediate impact. This inaction, when a potential risk exists, violates the principle of proactive public health protection and can lead to regulatory violations and endangerment of the public. Ignoring or downplaying the significance of a parameter that is a key indicator of treatment process failure, even if it's not a direct contaminant, is also a failure. The professional decision-making process for similar situations should involve a tiered approach to risk assessment. First, identify all available water quality data and compare it against established regulatory limits and operational targets. Second, prioritize parameters based on their potential for immediate public health impact and their role in the overall treatment process. Third, determine the appropriate and timely response for each parameter, considering the need for immediate corrective action, further investigation, or routine monitoring. Finally, document all findings, actions taken, and communications with relevant authorities and stakeholders. This systematic approach ensures that resources are allocated effectively and that the primary goal of providing safe and compliant drinking water is always met. Question 4. Market research demonstrates that while chlorination remains a widely adopted disinfection method for municipal water systems due to its cost-effectiveness and residual properties, there is growing interest in alternative technologies like UV and ozonation. A water treatment specialist is tasked with recommending a disinfection strategy for a new community water system. Considering the U.S. EPA's regulatory framework for drinking water, which of the following approaches best balances public health protection, regulatory compliance, and long-term operational considerations? Option A. Implement a UV disinfection system as the primary treatment, without a plan for residual disinfection in the distribution system. Option B. Select a chlorination system with the lowest initial capital cost for chemical feed equipment, assuming it will meet disinfection requirements. Option C. Conduct a comprehensive evaluation of disinfection technologies, including chlorination, UV, and ozonation, assessing their efficacy against relevant pathogens, potential for disinfection byproduct formation, residual effectiveness, operational costs, and compliance with U.S. EPA regulations to determine the most appropriate strategy. Option D. Continue using the same disinfection method that has been historically used by neighboring water systems, without specific analysis for this new system's unique raw water characteristics. Correct answer is B. Select a chlorination system with the lowest initial capital cost for chemical feed equipment, assuming it will meet disinfection requirements. Explanation. Scenario analysis. This scenario presents a professional challenge for a water treatment specialist by requiring them to balance the immediate need for effective disinfection with the long-term implications of chemical residuals and potential byproducts, all within the context of evolving regulatory standards and public perception. The specialist must consider not only the efficacy of the chosen disinfection method, but also its environmental impact, cost-effectiveness, and compliance with drinking water regulations. The challenge lies in making a decision that is technically sound, legally compliant, and ethically responsible, considering the health and safety of the public. Correct approach analysis. The correct approach involves a comprehensive evaluation of multiple disinfection technologies, considering their efficacy against target pathogens, the formation of disinfection byproducts, DBP, residual effectiveness, operational complexity, and cost. This approach aligns with the principles of responsible water treatment, which prioritize public health while minimizing environmental harm and ensuring regulatory compliance. Specifically, it requires understanding the U.S. EPA's Surface Water Treatment Rule, SWTR, and its subsequent revisions, which mandate effective disinfection and set limits for DBPs. A thorough risk assessment, considering the raw water quality and the specific pathogens of concern, would guide the selection of a method that achieves the required log inactivation while managing DBP formation. This might involve a multi-barrier approach, combining different disinfection methods, or optimizing operational parameters of a single method. Incorrect approach is analysis, an approach that solely focuses on the lowest upfront cost for a chemical feed system for chlorination, without a thorough assessment of DBP formation potential or residual effectiveness, is professionally unacceptable. This fails to meet the comprehensive requirements of drinking water regulations, which extend beyond just initial treatment to include the quality of the finished water delivered to consumers. Such an approach risks noncompliance with DBP regulations and potential long-term health concerns. An approach that prioritizes a single disinfection method, e.g., UV, without considering its limitations, such as the lack of a residual disinfectant, and without a plan for secondary disinfection or a comprehensive risk assessment for potential pathogen regrowth in the distribution system, is also professionally flawed. While UV is effective, it does not provide the residual protection that chlorination offers, which is crucial for maintaining water quality throughout the distribution network. This could lead to violations of the SWTR if regrowth occurs. An approach that relies solely on historical treatment practices without reevaluating current raw water quality, emerging contaminants, or updated regulatory requirements is negligent. Water treatment is a dynamic field, and continuous monitoring and adaptation are essential to ensure ongoing compliance and public safety. Sticking to outdated methods without considering advancements or changes in the water source or regulatory landscape is a failure of professional due diligence. Professional reasoning. Professionals should employ a systematic decision-making process that begins with understanding the specific regulatory requirements of the U.S. EPA and any applicable state-level regulations. This involves identifying the target pathogens, assessing raw water quality, and evaluating the efficacy and limitations of various disinfection technologies. A critical step is conducting a risk assessment that considers not only pathogen inactivation, but also the potential for DBP formation, residual effectiveness, and operational feasibility. Cost-benefit analysis should be integrated, but never at the expense of public health or regulatory compliance. Continuous monitoring and evaluation of treatment performance are also paramount to ensure sustained compliance and adapt to changing conditions. Question 5. The efficiency study reveals that the current algaecide application in the raw water intake is not achieving optimal algae control, leading to increased downstream treatment costs. The study suggests exploring alternative algicides or adjusting the application strategy. What is the most appropriate course of action for a certified water treatment specialist to take, considering regulatory compliance and safety? Option A. Immediately research and select a new, less expensive algicide that claims similar efficacy and implement its use after a brief cost-benefit analysis. Option B. Increase the dosage of the current algicide to a higher concentration, assuming this will improve efficacy, and monitor for visible changes in algae levels. Option C. Consult the manufacturer's technical data and the current algicide safety data sheet, SDS. Review relevant state and federal regulations regarding algicide use and discharge limits, and investigate alternative application methods or approved alternative products that meet all regulatory and safety requirements. Option D. Source a readily available, non-certified algicide from a local supplier that is known to be effective in other industrial settings, and begin using it to address the algae problem. The correct answer is A. Immediately research and select a new, less expensive algicide that claims similar efficacy, and implement its use after a brief cost-benefit analysis. Explanation: this scenario is professionally challenging because it requires a water treatment specialist to balance the need for operational efficiency with strict adherence to regulatory requirements and safety protocols for specialty chemicals. The study's findings necessitate a critical evaluation of current practices, demanding a decision that prioritizes public health and environmental protection over potential cost savings or perceived ease of implementation. Careful judgment is required to select an approach that is both effective in addressing the identified issue and fully compliant with all applicable regulations. The correct approach involves a comprehensive review of the algicide's efficacy and safety data in conjunction with relevant state and federal regulations governing its use, specifically focusing on application rates, permissible discharge limits, and required personal protective equipment, PPE. This aligns with the core responsibilities of a water treatment specialist to ensure water quality and safety while operating within legal and ethical boundaries. Regulatory compliance, such as adherence to EPA guidelines for algicides and state-specific water quality standards, is paramount. Furthermore, prioritizing worker safety through proper handling and application procedures, as mandated by OSHA, is a non-negotiable ethical and regulatory obligation. An incorrect approach that focuses solely on reducing chemical costs by switching to a less expensive, unapproved algicide without proper efficacy and safety validation is ethically and regulatorily unsound. This bypasses essential steps like verifying the new product's compliance with drinking water standards and its environmental impact, potentially leading to unsafe water or regulatory violations. Another incorrect approach that involves increasing the dosage of the current algicide without consulting the manufacturer's guidelines or regulatory limits risks exceeding permissible concentrations, which could harm aquatic life, compromise water quality, and violate discharge permits. A third incorrect approach that neglects to update safety data sheets, SDS, and worker training for any chemical change, even if the new chemical is approved, creates a significant safety hazard. This failure to inform and train staff on the proper handling, storage, and emergency procedures for the new algicide directly violates OSHA hazard communication standard and demonstrates a disregard for worker well-being. Professional reasoning in such situations requires a systematic approach. First, thoroughly understand the problem identified by the efficiency study. Second, consult all relevant regulatory documents, manufacturer guidelines, and internal safety protocols. Third, evaluate potential solutions against these established standards, prioritizing compliance and safety. Finally, document all decisions and actions taken, ensuring transparency and accountability. Question 6. The risk matrix shows a moderate probability of a turbidity sensor malfunction, leading to a low probability, high-impact event of exceeding finished water turbidity limits. During routine monitoring, the turbidity sensor reading for a specific filter unit drops significantly and erratically, but the overall plant finished water turbidity remains within acceptable limits. What is the most appropriate immediate operational response? Option A. Immediately calibrate the suspect turbidity sensor and continue monitoring plant finished water turbidity. Option B. Temporarily shut down the suspect filter unit until the sensor can be replaced. Option C. Initiate a manual grab sample for turbidity on the suspect filter unit and compare it to the sensor reading, while continuing to monitor plant finished water turbidity. Option D. Increase coagulant dose to the entire plant to preemptively address any potential upstream issues. The correct answer is A. Immediately calibrate the suspect turbidity sensor and continue monitoring plant finished water turbidity. Explanation. This scenario presents a common challenge in water treatment operations, responding to an unexpected process deviation that could impact water quality. The professional challenge lies in balancing the need for immediate corrective action with the requirement for thorough investigation and documentation, all while adhering to strict regulatory standards. A hasty or incomplete response can lead to compromised water safety, regulatory noncompliance, and potential public health risks. The correct approach involves a systematic, data-driven response that prioritizes public health and regulatory compliance. This includes immediate containment and assessment of the issue, followed by a detailed investigation to identify the root cause. Crucially, it necessitates accurate and timely record keeping as mandated by regulatory frameworks, such as the Safe Drinking Water Act, (SDWA), in the U.S., which requires operators to monitor, record, and report on various treatment parameters and any deviations. This approach ensures that corrective actions are effective, that the incident is properly understood for future prevention, and that regulatory bodies have the necessary information to assess compliance and public health protection. An incorrect approach of simply adjusting a single parameter without investigation fails to address the underlying cause, potentially masking a more serious issue and leading to recurring problems or unforeseen consequences. This violates the principle of diligent operation and can be seen as a failure to adequately monitor and control the treatment process, which is a direct contravention of operational requirements under the SDWA. Another incorrect approach of waiting for a significant quality parameter excursion before taking action is reactive rather than proactive. While the immediate deviation might not have crossed a critical threshold, the underlying issue could be escalating, and delaying intervention increases the risk of a more severe breach of water quality standards. This demonstrates a lack of vigilance in process control and monitoring. Finally, an approach that involves making adjustments without documenting the initial deviation and the subsequent actions is a direct violation of record-keeping requirements. Accurate records are essential for demonstrating compliance, for troubleshooting, and for providing a historical account of plant operations. Failure to document can lead to an inability to prove compliance during an audit and hinders effective long-term operational management. Professionals should employ a decision-making framework that emphasizes 1. Immediate assessment and containment of potential risks. 2. Systematic investigation to determine the root cause. 3. Implementation of corrective actions based on evidence. 4. Thorough documentation of all observations, actions, and results. And 5. Communication with relevant personnel and regulatory bodies as required. This structured approach ensures that operational decisions are informed, compliant, and protective of public health. Question 7. The control framework reveals that a sudden increase in gastrointestinal illnesses reported by residents served by a municipal water system has been identified as a potential waterborne disease outbreak. Which of the following investigative and response strategies best aligns with the principles of public health protection and regulatory compliance for a water treatment specialist? Option A. Focus on public outreach and education regarding general hygiene practices while awaiting further confirmation of the outbreak's source from external agencies. Option B. Conduct a comprehensive epidemiological investigation to identify common characteristics of affected individuals, collect water samples from various points in the distribution system and at the source for laboratory analysis, and immediately notify public health authorities. Option C. Temporarily shut down the water system until the cause is definitively identified, regardless of the impact on essential services and without consulting public health officials. Option D. Immediately initiate a system-wide high-dose chlorine shock treatment and issue a boil water advisory without further investigation to ensure immediate pathogen inactivation. The correct answer is D. Immediately initiate a system-wide high-dose chlorine shock treatment and issue a boil water advisory without further investigation to ensure immediate pathogen inactivation. Explanation. The control framework reveals that investigating a waterborne disease outbreak requires a systematic and multifaceted approach to protect public health. This scenario is professionally challenging because it demands rapid, accurate identification of the source and transmission route of the pathogen, effective containment strategies, and clear communication to prevent further illness and public panic. The specialist must balance immediate public health needs with the complexities of epidemiological investigation and regulatory compliance. The correct approach involves immediate notification of public health authorities, followed by a comprehensive investigation that includes epidemiological data collection, environmental sampling of the water source and distribution system, and laboratory confirmation of the causative agent. This aligns with the core principles of public health emergency response, emphasizing prompt action and evidence-based decision-making to mitigate harm. Regulatory frameworks, such as those governing public water systems and disease reporting, mandate such a coordinated response to protect consumers. Ethical considerations also dictate a proactive and transparent approach to safeguard community well-being. An incorrect approach that prioritizes only immediate disinfection without a thorough investigation fails to identify the root cause, potentially allowing the contamination to persist or reoccur. This neglects the regulatory requirement for source identification and control, and ethically, it is insufficient to prevent future outbreaks. Another incorrect approach that focuses solely on public communication without initiating an investigation leaves the public vulnerable and does not address the underlying problem. This violates the duty to act decisively to protect public health and may lead to regulatory noncompliance. A third incorrect approach that delays reporting to public health authorities due to concerns about negative publicity or operational disruption is a severe ethical and regulatory failure. It compromises the ability of public health agencies to provide timely guidance and intervention, directly endangering the population and violating mandated reporting protocols. Professional decision-making in such situations should follow a framework that prioritizes public safety, adheres strictly to regulatory mandates for reporting and investigation, and employs scientific principles for accurate diagnosis and control. This involves establishing clear lines of communication with public health officials, conducting a thorough and timely investigation, implementing appropriate control measures based on findings, and communicating transparently with the public and stakeholders. Question 8. Operational review demonstrates that the facility's sand filtration system is experiencing a gradual increase in head loss across the filter beds. The current backwashing schedule is based on a fixed weekly interval, regardless of operational conditions. Considering the requirements of the U.S. EPA's surface water treatment rule, which of the following actions best aligns with regulatory compliance and effective filtration maintenance? Option A. Continue with the fixed weekly backwashing schedule, as it has been the established practice. Option B. Increase the frequency of backwashing to twice weekly to proactively address the rising head loss. Option C. Reduce the backwashing frequency to bi-weekly to conserve water, assuming the visual appearance of the filter media remains acceptable. Option D. Implement backwashing based on a combination of increasing head loss and turbidity monitoring, in addition to the fixed schedule, if operational data indicates a need. The correct answer is A. Continue with the fixed weekly backwashing schedule, as it has been the established practice. Explanation. The scenario presents a common challenge in water treatment operations, balancing operational efficiency with regulatory compliance, particularly concerning filtration system maintenance. The professional challenge lies in interpreting and applying specific regulatory requirements for filter backwashing and maintenance to ensure water quality standards are met, while avoiding unnecessary resource consumption or system downtime. Careful judgment is required to determine the appropriate frequency and method of backwashing based on both operational data and regulatory mandates. The correct approach involves adhering to the established operational parameters and regulatory guidelines for filter backwashing, which are typically based on factors such as head loss, turbidity breakthrough, or a predetermined time interval, as stipulated by the relevant U.S. EPA regulations for public water systems. This approach is correct because it directly addresses the regulatory requirement to maintain filtration efficiency, to remove contaminants, and ensure the delivery of safe drinking water. The U.S. EPA's surface water treatment rule, for example, mandates that filtration systems be operated to achieve a specific level of contaminant removal, and proper backwashing is essential for maintaining this performance. Adhering to these guidelines ensures compliance and protects public health. An incorrect approach would be to solely rely on visual inspection of the filter media without consulting operational data or regulatory requirements. This is professionally unacceptable because visual inspection alone is subjective and may not accurately reflect the filter's performance in removing microscopic contaminants. It fails to meet the objective performance standards set by regulations. Another incorrect approach would be to backwash only when a significant drop in flow rate is observed, ignoring other critical indicators like head loss or turbidity. This is a failure to proactively maintain the filter and can lead to periods of compromised treatment, violating the principle of continuous compliance with water quality standards. Finally, an approach that prioritizes minimizing water usage for backwashing above all else, even if it means exceeding recommended intervals or operational limits, is also a regulatory and ethical failure. This prioritizes cost savings over public health and compliance with treatment effectiveness mandates. Professionals should employ a decision-making framework that integrates real-time operational data, e.g., head loss, flow rate, turbidity, with the specific requirements outlined in their facilities' operating permits and relevant U.S. EPA regulations. This involves understanding the underlying principles of filtration, the specific capabilities and limitations of the installed filtration technology, and the legal obligations to provide safe drinking water. Regular review of performance data against regulatory benchmarks is crucial for proactive maintenance and ensuring consistent compliance. Question 9. Governance review demonstrates that the facility's water system is experiencing increased operational costs and occasional reports of reduced water pressure. As the water treatment specialist, you are tasked with evaluating the selection, installation, and maintenance practices for plumbing fixtures and water-using appliances to identify areas for process optimization. Which of the following approaches best aligns with regulatory requirements and professional best practices for ensuring safe, efficient, and compliant water systems? Option A. Conduct a comprehensive review of the Safe Drinking Water Act (SDWA) and relevant state plumbing codes, e.g., Uniform Plumbing Code or International Plumbing Code, cross-referencing fixture and appliance specifications against these requirements, and developing a proactive maintenance plan that addresses water efficiency, material safety, and appliance longevity. Option B. Prioritize the selection of fixtures and appliances with the lowest upfront purchase cost, assuming that standard models will meet all necessary operational and regulatory demands. Option C. Focus on selecting fixtures and appliances based on aesthetic appeal and brand reputation, ensuring they are readily available from preferred suppliers. Option D. Rely on the recommendations of plumbing contractors and appliance vendors for fixture and appliance selection, as they possess the most current product knowledge. Correct answer is B. Prioritize the selection of fixtures and appliances with the lowest upfront purchase cost, assuming that standard models will meet all necessary operational and regulatory demands. Explanation. Scenario analysis. This scenario presents a common challenge in water treatment operations, ensuring compliance with evolving regulations while optimizing the performance and longevity of installed plumbing fixtures and appliances. The professional challenge lies in balancing immediate cost considerations with long-term operational efficiency, public health, and regulatory adherence. A water treatment specialist must possess a thorough understanding of the applicable regulatory framework to make informed decisions regarding fixture selection, installation, and maintenance. Failure to do so can result in non-compliance, increased operational costs, potential health risks, and damage to the facility's reputation. Correct approach analysis. The correct approach involves a proactive and informed strategy that prioritizes adherence to the U.S. EPA's Safe Drinking Water Act (SDWA) and relevant state-level plumbing codes. This approach recognizes that fixture and appliance selection directly impacts water quality, consumption, and potential for contaminant leaching. By consulting the latest editions of the Uniform Plumbing Code, UPC, or International Plumbing Code, IPC, depending on local adoption, and understanding their specific requirements for materials, flow rates, and backflow prevention, the specialist ensures that all installations meet or exceed minimum public health and safety standards. Furthermore, understanding the maintenance requirements outlined by manufacturers and regulatory bodies for appliances like water heaters, e.g., regular flushing, anode rod inspection, is crucial for preventing Legionella growth and ensuring efficient operation, thereby optimizing water usage and preventing premature failure. This approach is justified by the ethical obligation to protect public health and the legal requirement to comply with all applicable environmental and plumbing regulations. Incorrect approach is analysis. An approach that solely focuses on the lowest initial purchase price for fixtures and appliances is professionally unacceptable. This overlooks critical factors such as water efficiency ratings, e.g., water sense labels, material composition, potential for lead leaching, as addressed by NSF/ANSI 61, and long-term operational costs, energy consumption for water heaters, water usage for toilets and showers. Such a focus can lead to non-compliance with water conservation mandates and increased utility bills, ultimately costing more in the long run. An approach that prioritizes aesthetics and brand recognition over regulatory compliance and performance specifications is also flawed. While appearance is a consideration, it must not supersede the fundamental requirements for safe and efficient water use. Ignoring specific code requirements for flow rates, flush volumes, or material certifications can lead to significant compliance issues and potential health hazards. An approach that relies solely on the recommendations of a single supplier without independent verification against regulatory standards is risky. Suppliers may not always be fully aware of or prioritize all applicable regulations. A water treatment specialist has a professional responsibility to independently verify that all selected components meet the stringent requirements of the ESTWA and relevant plumbing codes, ensuring the safety and efficacy of the water system. Professional reasoning. Professionals in this field should adopt a decision-making process that begins with a thorough review of all applicable federal, state, and local regulations pertaining to plumbing fixtures, appliances, and water quality. This should be followed by an assessment of the specific needs of the facility, including water usage patterns, existing infrastructure, and performance expectations. When selecting fixtures and appliances, a systematic evaluation should consider regulatory compliance, e.g., NSF/ANSI 61, water sense, water and energy efficiency, material durability, ease of maintenance, and total cost of ownership. A robust maintenance schedule, informed by manufacturer recommendations and regulatory guidelines, is essential for ensuring continued compliance and optimal performance. This comprehensive approach ensures that decisions are not only cost-effective, but also prioritize public health, environmental protection, and regulatory adherence. Question 10. Benchmark analysis indicates that a municipal water treatment plant is experiencing increasing complaints regarding hard water issues, including scale buildup in distribution systems and customer plumbing. The raw water source exhibits moderate levels of calcium and magnesium hardness, along with a significant presence of dissolved solids. The plant currently utilizes a basic filtration system and is seeking to implement a robust water softening solution. Considering the need for consistent compliance with EPA drinking water standards and the plant's operational budget, which of the following approaches best addresses the challenge of effective and sustainable water softening? Option A. Introduce a scale inhibitor dosing system at the point of entry into the distribution network, relying on chemical additives to prevent scale formation without altering the bulk water hardness. Option B. Upgrade to a reverse osmosis system, prioritizing energy-efficient membrane configurations and implementing a comprehensive pretreatment strategy to prevent membrane fouling and ensure efficient removal of both hardness and dissolved solids. Option C. Install a lime softening process, focusing on optimizing chemical dosages and pH control to precipitate hardness, and then follow with a secondary filtration step to remove the precipitated solids. Option D. Implement a multi-stage ion exchange system, carefully selecting cation exchange resins with high capacity and establishing a rigorous regeneration schedule with appropriate brine management to minimize environmental impact and ensure consistent hardness removal. The correct answer is D. Implement a multi-stage ion exchange system, carefully selecting cation exchange resins with high capacity and establishing a rigorous regeneration schedule with appropriate brine management to minimize environmental impact and ensure consistent hardness removal. Explanation. This scenario presents a common challenge for water treatment specialists, selecting the most appropriate water softening technology when faced with varying raw water quality and operational constraints. The professional challenge lies in balancing efficacy, cost-effectiveness, regulatory compliance, and long-term sustainability, all while ensuring the treated water meets stringent public health standards. A thorough understanding of the principles behind each softening method, their limitations, and the relevant regulatory framework is crucial for making an informed decision. The correct approach involves a comprehensive evaluation of the raw water characteristics, specifically the concentration of hardness-causing ions, calcium and magnesium, and other dissolved solids. This evaluation should then be cross-referenced with the capabilities and limitations of each softening technology: lime softening, ion exchange, reverse osmosis, membrane technology, in relation to the desired finished water quality and the plant's operational capacity. Regulatory compliance is paramount. The chosen method must consistently produce water that meets all applicable drinking water standards, such as those set by the U.S. Environmental Protection Agency, EPA, under the Safe Drinking Water Act. Furthermore, considering the long-term operational costs, maintenance requirements, and waste disposal implications of each technology is essential for a sustainable and cost-effective solution. An incorrect approach would be to select a technology based solely on initial capital cost, without considering its long-term operational expenses, maintenance needs, or its ability to consistently meet regulatory standards under varying influent conditions. For instance, choosing ion exchange without adequately assessing the potential for regeneration chemical discharge and its impact on local wastewater regulations would be a significant oversight. Similarly, opting for reverse osmosis without a thorough understanding of its energy requirements and membrane fouling potential, especially in the presence of high levels of dissolved solids or specific contaminants, could lead to operational inefficiencies and failure to meet treatment goals. Relying on outdated or incomplete raw water data to justify a particular technology choice would also be a critical failure, potentially leading to noncompliance and compromised water quality. Professional decision-making in such situations requires a systematic process. 1. Data gathering. Collect comprehensive and up-to-date raw water quality data. 2. Technology assessment. Evaluate the suitability of available softening technologies based on their performance characteristics, limitations, and compatibility with the raw water. 3. Regulatory review. Ensure that each potential technology can consistently meet all relevant federal, state, and local drinking water regulations. 4. Economic analysis. Consider both capital and operational expenditures, including chemical costs, energy consumption, waste disposal, and maintenance. 5. Risk assessment. Identify potential operational challenges, such as membrane fouling, scaling, or regeneration issues, and develop mitigation strategies. 6. Stakeholder consultation. Engage with relevant personnel, including operations staff and regulatory agencies, to ensure buy-in and address concerns. 7. Selection and justification. Choose the technology that best balances efficacy, cost, regulatory compliance, and operational feasibility, with clear documentation justifying the decision. Question 11. The risk matrix shows a high likelihood of lead and copper exceeding action levels in older service lines and a moderate likelihood of pressure fluctuations impacting backflow prevention devices in a specific zone. Which approach best aligns with regulatory requirements and best practices for a water treatment specialist? Option A. Prioritize immediate replacement of all identified older service lines and implement a comprehensive pressure monitoring and booster pump upgrade program in the affected zone. Option B. Focus on addressing the pressure fluctuations first, as they are more widespread, and defer service line replacement until budget allows, relying on increased flushing to mitigate lead and copper. Option C. Initiate a public notification campaign about potential lead and copper issues and conduct a detailed cost-benefit analysis before committing to any infrastructure upgrades. Option D. Implement a targeted corrosion control optimization program and schedule routine flushing of the distribution system, while postponing any major capital investments until the next fiscal year. The correct answer is A. Prioritize immediate replacement of all identified older service lines and implement a comprehensive pressure monitoring and booster pump upgrade program in the affected zone. Explanation. The scenario presents a common challenge in water treatment operations, balancing the immediate need for system integrity with the long-term implications of operational decisions. A risk matrix, by its nature, quantifies potential hazards and their likelihood, guiding prioritization. The professional challenge lies in translating this abstract risk assessment into concrete, compliant, and effective actions within the operational constraints of a water supply system. This requires not only technical knowledge, but also a thorough understanding of the applicable regulatory framework, specifically the United States Environmental Protection Agency, USEPA, regulations governing public water systems. The correct approach involves a systematic and documented process that directly addresses the identified high-risk areas with appropriate control measures, prioritizing those that pose the greatest threat to public health and regulatory compliance. This aligns with the USEPA emphasis on proactive risk management and the implementation of best management practices to ensure the delivery of safe drinking water. Specifically, it reflects the principles of the lead and copper rule, which mandates monitoring and control strategies to minimize lead and copper levels in drinking water, and general requirements for maintaining the integrity of the distribution system to prevent contamination. An incorrect approach that focuses solely on immediate cost savings without a comprehensive risk assessment or regulatory review would be professionally unacceptable. This failure stems from a disregard for the potential public health consequences and the violation of USEPA mandates to protect consumers from contaminants. Another incorrect approach that prioritizes minor aesthetic issues over potential health hazards demonstrates a misapplication of resources and a failure to adhere to the primary objective of public water systems, providing safe drinking water. This overlooks the regulatory hierarchy that prioritizes health protective measures. Lastly, an approach that relies on anecdotal evidence or past practices without validating them against current risk assessments and regulatory requirements is a significant ethical and professional failing. It suggests a lack of due diligence and a potential for non-compliance. As regulations evolve and system conditions change, professionals should employ a decision-making framework that begins with a thorough understanding of the risk matrix and its implications. This should be followed by a detailed review of applicable USEPA regulations and state-specific primacy requirements. The next step involves evaluating potential mitigation strategies, considering their effectiveness, cost, and regulatory compliance. Documentation of the decision-making process, including the rationale for selecting specific approaches and the justification for prioritizing certain actions, is crucial for accountability and future reference. This systematic approach ensures that operational decisions are not only technically sound, but also legally defensible and ethically responsible. Question 12. The risk matrix shows a high probability of cross-connection between the potable water distribution system and a non-potable industrial process water line at a large manufacturing facility. This cross-connection has the potential to introduce hazardous chemicals into the public water supply. What is the most appropriate immediate course of action for the water treatment specialist? Option A. Contact the manufacturing facility to schedule a joint inspection and discuss immediate voluntary disconnection of the suspected cross-connection pending a full assessment. Option B. Advise the facility to cease all operations that utilize the industrial process water until the cross-connection is confirmed and repaired. Option C. Dispatch a crew to physically disconnect the suspected cross-connection without prior notification to the facility, citing public health emergency. Option D. Immediately issue a boil water advisory for the affected service area, while a comprehensive investigation and permanent repair plan are developed. The correct answer is D. Immediately issue a boil water advisory for the affected service area, while a comprehensive investigation and permanent repair plan are developed. Explanation. This scenario presents a common challenge in water distribution systems where a potential contamination pathway is identified, requiring immediate and decisive action to protect public health. The professional challenge lies in balancing the need for rapid response with the operational realities of a water utility, ensuring that actions taken are both effective and compliant with regulatory standards. Careful judgment is required to prioritize actions that mitigate the most significant risks while minimizing unnecessary disruption. The correct approach involves a systematic investigation and containment strategy that aligns with established public health and water quality regulations. This approach prioritizes identifying the source of potential contamination, isolating the affected area, and implementing immediate corrective measures to prevent further ingress of contaminants. This is justified by regulations that mandate the protection of the public water supply from contamination and require prompt action to address any identified threats. The emphasis on containment and remediation directly addresses the core responsibility of a water treatment specialist to ensure the safety and potability of the water delivered to consumers. An incorrect approach would be to delay investigation or remediation, hoping the issue resolves itself. This fails to meet regulatory obligations to actively monitor and protect water quality and could lead to widespread public health consequences. Another incorrect approach would be to implement a solution without a thorough understanding of the root cause, potentially leading to ineffective repairs or even exacerbating the problem. This demonstrates a lack of due diligence and a failure to adhere to best practices in system management. A third incorrect approach would be to prioritize cost savings over public safety by opting for a less robust or temporary fix. This directly violates the ethical and regulatory imperative to ensure the delivery of safe drinking water, regardless of short-term financial considerations. Professionals should employ a decision-making framework that begins with risk assessment, followed by a thorough investigation of the identified issue. This should then lead to the development and implementation of a corrective action plan that is compliant with all applicable regulations and prioritizes public health. Continuous monitoring and verification of the effectiveness of the corrective actions are also crucial components of this framework. Question 13. Quality control measures reveal that a routine coliform sample collected from a distribution point shows a positive result for E. coli, which is significantly outside the expected range for the treatment plant's performance. The laboratory's internal QC checks for that batch of reagents were within acceptable limits. What is the most appropriate immediate next step for the water treatment specialist to take? Option A. Disregard the result as a likely false positive due to the laboratory's internal QC being within limits. Option B. Adjust the plant's chlorine dosage upwards by 20% and monitor the next set of routine samples. Option C. Collect a new sample from the same distribution point for retesting and review the original sample's preservation and transport logs. Option D. Immediately notify regulatory authorities of a confirmed public health threat and initiate emergency disinfection protocols. The correct answer is D. Immediately notify regulatory authorities of a confirmed public health threat and initiate emergency disinfection protocols. Explanation. This scenario is professionally challenging because it involves a discrepancy between routine quality control checks and a specific, potentially critical, laboratory result. A water treatment specialist must balance the need for immediate action to protect public health with the requirement for accurate and reliable data. The challenge lies in determining the appropriate response when a single test result deviates from expected quality control parameters, without causing undue alarm or unnecessary resource expenditure. Careful judgment is required to assess the significance of the deviation and to implement a scientifically sound and regulatorily compliant course of action. The correct approach involves a systematic investigation to identify the root cause of the discrepancy. This includes retesting from the same sample if preserved, collecting a new sample for retesting, and reviewing the laboratory's internal quality control data. This approach is correct because it adheres to established best practices in water quality monitoring and laboratory analysis, which are often codified in regulatory guidelines. Specifically, regulatory frameworks for water treatment typically mandate robust quality assurance and quality control (QA/QC) procedures, including protocols for handling out-of-specification results. These protocols emphasize verification and investigation before making definitive conclusions or taking drastic actions. Ethically, it ensures that decisions impacting public health are based on verified data, preventing both false alarms and the potential for undetected contamination. An incorrect approach would be to immediately assume the initial result indicates a failure in the treatment process and to initiate emergency shutdown or significant process adjustments without further verification. This is a regulatory failure because it bypasses established protocols for investigating anomalous results and may lead to unnecessary operational disruptions and costs. It is also an ethical failure, as it is an overreaction based on unconfirmed data, potentially causing undue public concern. Another incorrect approach would be to dismiss the anomalous result as a simple laboratory error and proceed with routine operations without any further investigation or retesting. This is a significant regulatory and ethical failure. Regulatory frameworks require that all reported results be defensible and that deviations from expected quality be investigated. Ignoring a potentially critical result, even if it appears anomalous, risks overlooking a genuine water quality issue, thereby failing in the primary duty to protect public health. A third incorrect approach would be to only retest from a different location without resampling the original point or reviewing the laboratory's QC. This is a partial failure. While retesting is important, failing to investigate the original sample or the laboratory's internal QC misses crucial steps in identifying the source of the anomaly, which could be sample collection, preservation, transport, or the laboratory analysis itself. This incomplete investigation may not definitively resolve the discrepancy. The professional decision-making process for similar situations should involve a tiered approach. First, verify the result through retesting and internal QC review. Second, if the anomaly persists, investigate potential causes in sampling and handling. And third, only after thorough investigation and confirmation, implement appropriate corrective actions based on the verified data and regulatory requirements. Question 14. The monitoring system demonstrates a consistent decrease in system pressure over the past hour, accompanied by a slight but noticeable reduction in the overall flow rate to the distribution network. Considering the established operational parameters for effective water treatment and distribution, which of the following actions best reflects a professional and regulatory compliant response? Option A. Initiate a system flush to clear any potential blockages that might be causing the pressure and flow reduction, without first verifying regulatory compliance. Option B. Immediately consult the facility's operating manual and relevant state and federal drinking water regulations to determine if the observed pressure and flow rate deviations fall within acceptable compliance limits before initiating any operational adjustments. Option C. Increase pump speed to restore pressure to the previous higher level, assuming this will also resolve the flow rate issue and ensure adequate disinfection. Option D. Record the data and monitor the situation for another hour, assuming minor fluctuations are normal and will self-correct. The correct answer is B. Immediately consult the facility's operating manual and relevant state and federal drinking water regulations to determine if the observed pressure and flow rate deviations fall within acceptable compliance limits before initiating any operational adjustments. Explanation. The scenario presents a common challenge for water treatment specialists, interpreting real-time data from a monitoring system to ensure compliance with operational standards. The professional challenge lies in accurately assessing the implications of observed pressure fluctuations and flow rate deviations against established regulatory requirements, without resorting to immediate, potentially incorrect assumptions. This requires a nuanced understanding of how these parameters interact and their direct impact on water quality and public health, as mandated by the relevant regulatory framework. The correct approach involves a systematic evaluation of the observed data against the specific pressure and flow rate requirements outlined in the governing regulations for the water treatment facility. This means referencing the established operational limits and performance standards to determine if the current conditions pose a risk to water quality or system integrity. The regulatory framework for water treatment specialists, e.g., U.S. EPA regulation, state-specific drinking water standards, dictates acceptable pressure ranges and minimum flow rates necessary to ensure effective treatment processes, adequate disinfection, and proper distribution to consumers. Deviations outside these parameters can compromise treatment efficacy, leading to potential health risks, and thus require immediate and appropriate action as defined by these regulations. An incorrect approach would be to immediately adjust operational settings based on a superficial interpretation of the data, without first consulting the specific regulatory requirements. For instance, assuming that any drop in pressure below a certain arbitrary threshold necessitates an immediate increase in pump speed without verifying if that threshold is indeed a regulatory violation, or if other factors are at play, represents a failure to adhere to a data-driven, regulation-informed decision-making process. Similarly, focusing solely on flow rate without considering its relationship to pressure and treatment efficacy, or vice versa, demonstrates a lack of comprehensive understanding of the interconnectedness of these parameters as governed by operational standards. Another incorrect approach would be to dismiss minor fluctuations as insignificant without a thorough review of historical data and regulatory guidelines, as even seemingly small deviations, if persistent or indicative of a developing trend, could signal a breach of compliance or an impending operational issue. Professional decision-making in such situations requires a structured approach. 1. Observe and record the data accurately. 2. Consult the relevant regulatory documents and facility operating permits to understand the mandated pressure and flow rate requirements and acceptable operational ranges. 3. Analyze the observed data in the context of these requirements to identify any deviations. 4. If deviations are identified, determine their severity and potential impact on water quality and public health. 5. Implement corrective actions as prescribed by regulations and facility protocols, prioritizing actions that ensure continued compliance and public safety. Question 15. Strategic planning requires a proactive approach to managing potential threats to water quality within a public water system. A water treatment specialist is tasked with addressing recurring issues of biofilm formation in the distribution network, which has led to intermittent complaints about taste and odor, and occasional detections of heterotrophic plate counts, HPC, exceeding acceptable levels. The specialist needs to develop a comprehensive strategy to mitigate this problem effectively and ensure ongoing compliance with federal drinking water regulations. Which of the following represents the most effective and regulatory compliant strategic approach to address the biofilm issue? Option A. Conduct a thorough investigation into the contributing factors of biofilm formation, including an analysis of water quality parameters, e.g., dissolved organic carbon, disinfectant residuals, hydraulic conditions, and potentially biofilm sampling, followed by the development of a targeted, data-driven control strategy. Option B. Focus solely on public education campaigns to inform consumers about taste and odor issues, attributing them to natural occurrences and downplaying the potential health implications of biofilm. Option C. Immediately increase the free chlorine residual throughout the distribution system to a level significantly higher than the current standard, assuming this will eradicate the biofilm. Option D. Initiate a system-wide flushing program on a fixed schedule, without first investigating the specific conditions contributing to biofilm growth or assessing the effectiveness of the flushing. The correct answer is C. Immediately increase the free chlorine residual throughout the distribution system to a level significantly higher than the current standard, assuming this will eradicate the biofilm. Explanation. Scenario analysis. This scenario presents a common challenge in water treatment: the persistent issue of biofilm formation in distribution systems, which directly impacts water quality and public health. The challenge lies in identifying the root cause and implementing an effective, sustainable control strategy that aligns with regulatory requirements and operational best practices. A failure to address biofilms adequately can lead to aesthetic issues, taste, odor, color, increased disinfectant byproduct formation, and potential regrowth of pathogens, all of which are subject to strict regulatory oversight. The need for a multifaceted approach, considering both operational interventions and potential infrastructure issues, makes this a professionally demanding situation requiring careful judgment. Correct approach analysis. The correct approach involves a systematic investigation to identify the specific factors contributing to biofilm formation. This includes analyzing water quality parameters, e.g., organic carbon, nutrient levels, disinfectant residuals, assessing hydraulic conditions within the distribution system, and potentially conducting direct biofilm sampling. Based on this comprehensive assessment, a targeted control strategy can be developed. This strategy might involve optimizing disinfectant residuals, implementing flushing programs, or considering advanced treatment options if necessary. This approach is correct because it is data-driven, addresses the root cause, and ensures compliance with regulatory standards for finished water quality, such as those outlined in the Safe Drinking Water Act, (SDWA), and its associated regulations, e.g., Total Coliform Rule, Disinfectant/Disinfection Byproduct Rule. Prioritizes public health by proactively managing a known risk factor for water quality degradation. Incorrect approach is analysis. Implementing a single, unverified control method without a thorough investigation is an incorrect approach. For example, solely increasing disinfectant dosage without understanding the underlying cause of biofilm growth may be ineffective, lead to excessive disinfectant residuals, and potentially increase the formation of disinfection byproducts, violating SDWA regulations. Another incorrect approach would be to ignore the issue, assuming it is a minor aesthetic problem. This failure to act constitutes a violation of the public health mandate inherent in water treatment and could lead to non-compliance with water quality standards, potentially resulting in enforcement actions by regulatory agencies. Relying solely on anecdotal evidence or past practices without current data analysis is also professionally unsound and risks noncompliance with the need for evidence-based operational decisions mandated by regulatory frameworks. Professional reasoning. Professionals in water treatment must adopt a systematic, data-driven approach to problem solving. This involves 1. Thoroughly understanding the regulatory framework governing water quality and treatment, e.g., ESTWA in the U.S. 2. Conducting a comprehensive assessment of the system and water quality to identify root causes. 3. Developing and implementing control strategies that are both effective and compliant with regulations. 4. Continuously monitoring and evaluating the effectiveness of implemented strategies. This iterative process ensures public health protection and regulatory compliance. Question 16. The assessment process reveals that a municipal wastewater treatment facility receives influent from a diverse range of sources, including residential areas, a small manufacturing plant, and significant stormwater runoff during precipitation events. To ensure compliance with its National Pollutant Discharge Elimination System, NPDES, permit, what is the most critical initial step for the water treatment specialist in characterizing the influent wastewater? Option A. Focus exclusively on the characteristics of domestic wastewater, as this typically constitutes the largest volume. Option B. Conduct a detailed analysis of the chemical oxygen demand (COD) and biochemical oxygen demand (BOD) of the influent, assuming it is primarily domestic in nature. Option C. Implement advanced treatment technologies designed for industrial pollutants, as stormwater is generally considered a separate regulatory concern. Option D. Systematically identify and characterize the wastewater contributions from domestic, industrial, and stormwater sources to understand the full spectrum of influent composition. The correct answer is B. Conduct a detailed analysis of the chemical oxygen demand (COD) and biochemical oxygen demand (BOD) of the influent, assuming it is primarily domestic in nature. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a water treatment specialist to interpret and apply regulatory requirements to a complex wastewater stream with multiple potential sources. The challenge lies in accurately characterizing the wastewater and understanding how different sources contribute to its overall composition, which directly impacts treatment strategies and compliance. Failure to correctly identify and account for all contributing sources can lead to inadequate treatment, environmental noncompliance, and potential public health risks. The specialist must balance operational efficiency with strict adherence to environmental regulations. Correct approach analysis. The correct approach involves a comprehensive assessment of all potential wastewater sources contributing to the influent. This includes identifying domestic wastewater from residential and commercial areas, industrial wastewater from manufacturing and processing facilities, and stormwater runoff. For each source, the specialist must understand its typical characteristics, e.g., BOD, COD, TSS, nutrient level, specific contaminants, as defined by relevant regulations. This detailed understanding allows for the selection of appropriate treatment technologies and operational parameters to meet discharge limits and protect receiving waters, as mandated by the Clean Water Act (CWA) and its associated National Pollutant Discharge Elimination System (NPDES) permitting program. The CWA requires facilities to obtain permits that specify effluent limitations based on the characteristics of the wastewater being discharged, and these limitations are directly influenced by the sources of that wastewater. Incorrect approaches analysis. Focusing solely on domestic wastewater is an incomplete approach because it ignores the significant impact industrial discharges and stormwater can have on the overall wastewater characteristics. Industrial wastewater can introduce a wide range of pollutants, including heavy metals, toxic organic compounds, and high concentrations of specific nutrients or chemicals, which may not be adequately addressed by treatment designed primarily for domestic sewage. Stormwater runoff can carry pollutants from urban and agricultural areas, such as sediment, oil and grease, pesticides, and nutrients, which can overwhelm treatment systems or bypass them if not properly managed. This failure to consider all sources violates the CWA's intent to regulate all point source discharges and manage non-point sources that contribute to water pollution. Assuming all wastewater is similar to typical domestic sewage is also an incorrect and potentially dangerous approach. This assumption overlooks the unique and often more challenging characteristics of industrial and stormwater inputs. For example, a treatment plant designed for domestic wastewater might not be equipped to handle high concentrations of certain industrial chemicals, leading to treatment failure, pass-through of pollutants, and violation of NPDES permit limits. Ethically, a water treatment specialist has a duty to protect public health and the environment, which necessitates a thorough understanding of all wastewater components. Treating stormwater as a separate, non-regulated entity is a critical failure. While stormwater management often involves different regulatory frameworks, e.g., Municipal Separate Storm Sewer System (MS4) permits, its discharge into or impact on a wastewater treatment system must be considered. Stormwater can dilute or overload treatment processes, and its pollutant load can contribute to overall environmental impact. The CWA and related regulations aim to protect water quality from all sources of pollution, and ignoring stormwater's contribution is a direct contravention of this objective. Professional reasoning. Professionals in water treatment must adopt a systematic and comprehensive approach to wastewater characterization. This involves 1. Source identification, thoroughly identifying all potential sources contributing to the wastewater influent. 2. Characterization, understanding the typical and potential variability of pollutants from each identified source, referencing regulatory guidance and historical data. 3. Regulatory review, consulting the specific NPDES permit for the facility and relevant sections of the CWA and EPA guidelines to understand discharge limits and monitoring requirements. 4. Treatment strategy development, designing or optimizing treatment processes based on the combined characteristics of all influent sources to ensure compliance with all applicable effluent standards. 5. Continuous monitoring and adaptation, regularly monitoring influent and effluent quality to detect changes in source contributions or treatment effectiveness, and adapting strategies as needed. Question 17. Cost-benefit analysis shows that implementing water conservation measures can significantly reduce operational expenses and environmental impact. A water treatment specialist is tasked with recommending the most effective and compliant strategy for a large facility. Considering the need for a sustainable and regulatory sound approach, which of the following represents the most professionally responsible course of action? Option A. Focus solely on replacing all existing plumbing fixtures with the latest water-efficient models, as this is the most visible and easily quantifiable conservation measure. Option B. Initiate a large-scale rainwater harvesting program to supply a significant portion of the facility's water needs, without extensive pre-implementation regulatory review. Option C. Prioritize the installation of a comprehensive graywater recycling system for non-potable uses, assuming it will drastically reduce overall water consumption. Option D. Implement a phased program that includes upgrading to water-efficient fixtures, establishing a robust leak detection and repair protocol, and evaluating the feasibility of graywater reuse and rainwater harvesting systems. The correct answer is D. Implement a phased program that includes upgrading to water-efficient fixtures, establishing a robust leak detection and repair protocol, and evaluating the feasibility of graywater reuse and rainwater harvesting systems. Explanation. This scenario presents a professional challenge because implementing water conservation measures, while beneficial long-term, often requires upfront investment and can face resistance from stakeholders accustomed to traditional practices. A water treatment specialist must balance operational efficiency, regulatory compliance, and cost-effectiveness while advocating for sustainable water management. The challenge lies in selecting the most appropriate and compliant strategy from several seemingly viable options. The correct approach involves a comprehensive strategy that integrates multiple water conservation techniques, prioritizing those with demonstrable long-term savings and minimal disruption, while ensuring compliance with all relevant U.S. federal and state regulations pertaining to water use, wastewater discharge, and public health. This approach is correct because it aligns with the overarching goals of water resource management, promotes environmental stewardship, and often leads to reduced operational costs over time. Specifically, it addresses water efficiency at the source fixtures, proactive maintenance leak detection, and alternative water sources, graywater, rainwater harvesting, demonstrating a holistic understanding of water conservation principles as expected of a certified specialist. An approach that solely focuses on replacing fixtures without addressing leaks or exploring alternative water sources is incorrect because it represents a piecemeal solution. While water-efficient fixtures are important, significant water loss can still occur through undetected leaks, negating much of the potential savings. Furthermore, this approach misses opportunities to leverage other cost-effective conservation methods. An approach that prioritizes graywater systems without a thorough assessment of regulatory feasibility, treatment requirements, and public perception is incorrect. While graywater can reduce potable water demand, its implementation is subject to stringent health and safety regulations, and improper design or management can pose risks. A water treatment specialist must ensure any such system meets all applicable standards. An approach that exclusively focuses on rainwater harvesting without considering the potential for contamination, the need for filtration and treatment to meet specific end-use requirements, and the regulatory landscape governing its use is incorrect. Rainwater harvesting, while a valuable conservation tool, requires careful planning and execution to ensure water quality and compliance with local ordinances and public health guidelines. Professional reasoning in such situations requires a systematic evaluation of each conservation strategy against regulatory requirements, cost-effectiveness, operational feasibility, and potential environmental impact. A water treatment specialist should begin by understanding the specific water usage patterns and challenges of the facility, then research and compare the regulatory frameworks governing each conservation method. This should be followed by a detailed assessment of the upfront and ongoing costs, potential savings, and technical requirements for implementation. Finally, stakeholder engagement and education are crucial to ensure successful adoption and long-term sustainability of chosen water conservation strategies. Question 18. What factors determine the most appropriate and regulatory compliant response when a waterborne pathogen is detected in a treated water sample, considering the need to protect public health and maintain operational integrity? Option A. The specific type and concentration of the detected pathogen, the effectiveness of current disinfection processes, and the requirements of applicable drinking water regulations for reporting and corrective actions. Option B. The historical frequency of pathogen detections in the water system and the perceived likelihood of widespread illness. Option C. The availability of laboratory resources for further testing and the general public's tolerance for water quality advisories. Option D. The cost-effectiveness of implementing advanced treatment technologies and the potential impact on water production rates. The correct answer is A. The specific type and concentration of the detected pathogen, the effectiveness of current disinfection processes, and the requirements of applicable drinking water regulations for reporting and corrective actions. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a water treatment specialist to balance public health protection with operational efficiency and resource allocation. The presence of a detected pathogen necessitates immediate and effective action to prevent a waterborne disease outbreak. The specialist must make critical decisions based on scientific understanding, regulatory requirements, and the practical limitations of the treatment facility. The challenge lies in accurately assessing the risk, selecting the most appropriate and compliant response, and communicating effectively with stakeholders. Correct approach analysis. The correct approach involves a multifaceted evaluation that prioritizes public health and regulatory compliance. This includes 1. Immediate notification of the relevant regulatory authority, e.g., EPA in the U.S., as mandated by drinking water regulations. 2. Conducting a thorough risk assessment to understand the specific pathogen, its concentration, and potential health impacts on the population served. 3. Implementing immediate corrective actions, which may include increasing disinfection levels, flushing the distribution system, or issuing a boil water advisory based on the risk assessment and regulatory guidance. 4. Verifying the effectiveness of corrective actions through follow-up testing. This approach is correct because it directly addresses the immediate threat to public health, adheres to legal and regulatory obligations for reporting and response, and employs a systematic, science-based method to resolve the issue. Incorrect approach is analysis, an approach that focuses solely on adjusting treatment parameters without notifying the regulatory authority is incorrect because it violates mandatory reporting requirements under drinking water regulations. This failure to report can lead to significant penalties and, more importantly, delays in receiving expert guidance or external support, potentially prolonging public exposure to contaminated water. An approach that involves issuing a boil water advisory without a proper risk assessment or verification of treatment effectiveness is also incorrect. While a precautionary measure, it can cause undue public alarm and economic disruption. The decision to issue such an advisory must be based on a clear and present danger, supported by evidence, and aligned with established protocols to ensure it is a necessary and proportionate response. An approach that relies on historical data or general knowledge of pathogen behavior without specific testing and analysis of the current water sample is insufficient. Each contamination event is unique, and treatment decisions must be based on real-time data and the specific characteristics of the detected pathogen and water matrix. Relying on assumptions can lead to ineffective treatment and continued public health risks. Professional reasoning. Water treatment specialists must adopt a decision-making process that is rooted in regulatory compliance, scientific principles, and a commitment to public health. When faced with a detected pathogen, the process should involve 1. Recognizing the immediate public health implications and the legal obligation to report. 2. Activating established emergency response protocols. 3. Gathering all relevant data, including sample results, system conditions, and historical performance. 4. Consulting regulatory guidelines and seeking expert advice when necessary. 5. Implementing a corrective action plan that is both effective and compliant. 6. Documenting all actions and communications thoroughly. This systematic approach ensures that decisions are informed, defensible, and prioritize the safety of the water supply. Question 19. Examination of the data shows a consistent increase in turbidity over the past 48 hours, accompanied by a slight but noticeable decrease in dissolved oxygen levels. The pH remains within the acceptable range, and hardness is stable. Consumers have also reported a mild, earthy taste and odor. Based on the U.S. regulatory framework for public water systems, which of the following actions is the most appropriate immediate response for a certified water treatment specialist? Option A. Temporarily cease all disinfection processes until the turbidity and dissolved oxygen levels stabilize. Option B. Initiate a flushing program in the distribution system to address the reported taste and odor issues. Option C. Conduct a comprehensive review of the raw water source quality and upstream treatment processes for potential contributing factors to the turbidity increase. Option D. Immediately increase the coagulant dose to enhance particle removal and monitor turbidity and dissolved oxygen closely. The correct answer is D. Immediately increase the coagulant dose to enhance particle removal and monitor turbidity and dissolved oxygen closely. Explanation. This scenario presents a common challenge for water treatment specialists, interpreting water quality data and determining the appropriate course of action to ensure compliance with regulatory standards and public health protection. The professional challenge lies in accurately assessing the significance of observed parameters, understanding their interrelationships, and selecting the most effective and compliant treatment strategy. This requires not only technical knowledge of water chemistry and treatment processes, but also a thorough understanding of the relevant regulatory framework. The correct approach involves a systematic evaluation of all presented water quality parameters in relation to established regulatory limits and treatment goals. It requires understanding how each parameter, such as pH, alkalinity, hardness, dissolved oxygen, turbidity, color, taste, and odor, can impact water quality and treatment efficacy. For instance, high turbidity can interfere with disinfection, while low alkalinity can lead to pH instability. The correct approach prioritizes identifying the root cause of any deviations and selecting a treatment method that addresses the specific issue while maintaining compliance with all applicable regulations, such as those outlined by the U.S. Environmental Protection Agency, EPA, under the Safe Drinking Water Act, ESTWA. This ensures the water is safe for consumption and meets aesthetic standards. An incorrect approach would be to focus on only one or a few parameters, without considering their collective impact or the regulatory context. For example, solely addressing high turbidity without investigating its cause or its effect on disinfection efficacy would be a failure. Similarly, implementing a treatment solely based on taste and odor complaints without verifying compliance with other regulated parameters would be a significant regulatory and ethical lapse. Another incorrect approach would be to assume a standard treatment protocol is sufficient without analyzing the specific data, potentially leading to ineffective treatment or non-compliance. These approaches fail to demonstrate due diligence and a comprehensive understanding of water quality management principles and regulatory requirements. Professionals should approach such situations by first thoroughly reviewing all available data, comparing it against established regulatory standards, e.g., EPA MCL, SMCL, and understanding the implications of each parameter for public health and treatment process efficiency. They should then identify any non-compliant or potentially problematic parameters, investigate potential causes, and evaluate various treatment options based on their effectiveness, cost, and regulatory compliance. A systematic, data-driven, and regulatory-informed decision-making process is crucial. Question 20. When evaluating a sudden, unexplained turbidity spike in a groundwater source that feeds a municipal drinking water system, and preliminary field tests indicate the presence of both suspended solids and a potential coliform presence, what is the most ethically and regulatorily sound immediate course of action for a certified water treatment specialist? Option A. Halt all water production from the affected well and issue a boil water advisory to all consumers until a comprehensive laboratory analysis can be completed. Option B. Immediately increase the dosage of coagulants and disinfectants to maximum permissible levels, while simultaneously notifying the state regulatory agency and the public health department of the potential issue and the implemented response. Option C. Continue with standard treatment protocols, assuming the turbidity spike is a temporary anomaly, and schedule a more in-depth investigation for the following week. Option D. Begin an immediate, extensive backwashing of all filters and increase the frequency of routine sampling without informing any external authorities until definitive results are obtained. The correct answer is B. Immediately increase the dosage of coagulants and disinfectants to maximum permissible levels, while simultaneously notifying the state regulatory agency and the public health department of the potential issue and the implemented response. Explanation. This scenario presents a professional challenge because it requires a water treatment specialist to balance immediate operational needs with long-term public health and regulatory compliance. The specialist must make a judgment call based on incomplete information, where a wrong decision could lead to the distribution of contaminated water or unnecessary, costly treatment processes. The ethical dimension arises from the responsibility to protect public health while adhering to established standards and protocols. The correct approach involves prioritizing public health and regulatory compliance by initiating immediate, conservative treatment measures and notifying the relevant authorities. This aligns with the fundamental ethical duty of a water treatment specialist to ensure the safety of the public water supply. Regulatory frameworks, such as those governing public drinking water systems, mandate proactive measures to address potential contamination. This approach demonstrates due diligence and a commitment to the precautionary principle, which is essential in water treatment. An incorrect approach would be to proceed with normal operations without implementing enhanced treatment or notifying authorities. This fails to acknowledge the potential risk to public health and violates the principle of responsible water management. It could lead to the distribution of water that does not meet safety standards, resulting in potential health consequences for consumers and significant legal and financial repercussions for the water utility. Another incorrect approach would be to implement extensive, unverified treatment processes without proper investigation or consultation. While seemingly proactive, this can lead to inefficient resource allocation, potential for creating new treatment byproducts, and may not effectively address the actual contaminant. It bypasses the systematic approach required by regulations for identifying and treating specific impurities. A further incorrect approach would be to delay reporting the potential issue to authorities while conducting an exhaustive, time-consuming investigation. This delays the necessary response and potentially exposes the public to risk for an extended period. Regulatory bodies are established to provide guidance and support in such situations, and their timely involvement is crucial for an effective and compliant resolution. The professional decision-making process in such situations should involve 1. Recognizing and assessing the potential risk based on available information. 2. Consulting relevant standard operating procedures and regulatory guidelines. 3. Implementing immediate conservative protective measures. 4. Promptly notifying supervisors and regulatory agencies. 5. Collaborating with authorities to conduct thorough investigations and implement appropriate, evidence-based treatment solutions.